final example today will be really an AC generator problem. This is a very simple problem. Here we have an AC generator. It has a coil that has, this is really a very simple AC generator as well. Because generally the AC generators will have thousands of turns, and this one only has 10. But it has 10 turns, and it encloses an area of 1,200 square centimeters. And the coil rotates at a constant angular frequency of 60 hertz in a uniform magnetic field of 0.4 Tesla. And they want to know what's the peak EMF of the generator. Well, a generator is just this expression we've seen, as we've seen. The EMF is E naught, which is the maximum, the peak EMF, times sine omega t. Omega is the 2 pi times the frequency. In this case, we're given the frequency as 60 hertz. And if you remember, this E naught was a lumped expression for the number of turns times the magnetic field times the area enclosed times that frequency, that angular frequency. So it's just plugging in the numbers, really. And to get the maximum is N is 10, B naught was 0.4, A was 1,200 square centimeters. And again, we need to convert that. And I know that there's, in 1 meter, there's 100 centimeters, but to get rid of the square here, I'll have to square that conversion factor to convert it to square meters. And then omega here is 2 pi times 60 hertz, which is 60 per second. Remember, hertz is a per second. And when I did all of that, I got 181 Tesla meters squared per second. And in this particular case, it turns out to be a maximum voltage of 181 volts. Now, typical generators might be a much larger cross-sectional area and more turns. So they would, a typical value, say in a hydroelectric plant, might be 15,000 volts or something on that order for typical generators. So this is a relatively low voltage for the peak-to-peak, peak voltage. But again, kind of a simple formula once you know how to convert Tesla meters squared per second to volts, right? Volts.